Welcome everybody. JSON Parser. This feels like graduation day. It's been a long road. It's been a long road getting to this point, and we're here now. So we got Mike with us. Welcome, Mike.
Hello.
I know of no greater buddy to do this with. It is what it sounds like. If you take the challenge here, we're going to see that we're going to get a string. And it's a string that represents JSON. We might refer to that as a JSON string. And anything you can do in JSON is valid inside of the string. And what we're going to get out at the end is a type that corresponds to the string therein. So that means we're going to have to do some pretty fancy stuff. And this is going to be an extremely long challenge. Mike and I are expecting it to be about 2 hours. We'll see how it goes. We have 4 solutions to get through. And these are the people on GitHub. I guess for consistency, we don't need an @ there. But anywho. And then after that, we're going to do all of it all over again. But Mike has pre-prepared a solution for HKT Toolbelt, his library. Well, many people work on it, but the library that Mike started for higher kinded types, that's what the HKT part stands for. And within there, we're going to see like a really, I don't want to spoil it, but it's going to be super duper cool. So I think what we're going to do is probably record these. That's this video. That's part 1, is these 4. And then part 2 is going to be another video with that I'll post separately with Mike and I showing the HKT Toolbelt solution. Mike, how are you feeling?
I'm feeling great. I'm excited to get started.
Okay. So, you're not gonna solve it live, of course, because we have like a bajillion things to get through. But actually, I mean, we're basically going to go through a live solution that's part 2, I suppose, when we do it. So let me grab Alexsey. There we go. Oops. All right. So here's Alexsey's solution. It comes with this little disclaimer. So he said the solution is designed to pass more complicated test cases than the ones that are provided. Also, it's really easy to extend it to parse numbers as well. Not sure why it's been excluded from the problem set. So yeah, if we go back and we see it says numbers in Unicode escape and JSON can be ignored. You don't need to parse them. I think the reason is just someone was, the author. Who is the author anyway? Hydrati. Oh, okay. We're going to look at one from Hydrati. Actually, Hydrati had 3 solutions up. Well, anyway, it's just to sort of make it a little bit easier, I think. So, all right, Mike, where do you think we should start on this one?
Well, yeah. So all of these are going to be quite complicated, but starting at the beginning for the parse entry statement might be best. So we immediately see this parse value, which is going to be the type that converts a input to an atomic value. So either a undefined or null or true or false. So if we scroll down a little bit and if we look at a parse value, trim left is simple. We're just removing white space, leading white space. So parse value, we're checking at each step. Is it undefined? Is it null? Is it true? Is it false? Parsing these like atomic values. And then we get into, can we parse a string? Then we get into, can we parse a array? And then we can get into, can we parse an object? So that's kind of how this is structured. It's one big like switch case, essentially. And we're using these internal infer statements to get at what the contents of like the next string are, for example, on line 111.
Yep, we're using the infer there and then grabbing it. Okay. And always we're passing in, I noticed another common thing, like we have infer R, which is, I think, for rest. So we're kind of passing in the rest of the stuff, as a kind of ending section.
Yeah. Interesting. So one other interesting aspect of this is that parse value, its type if we can think of like, types in terms of like higher order types, the type of parse value is it takes in a string and it returns an array of 2 elements. The first element is going to be the parsed value, and the second element is going to be the rest of the input. So if we go back up to JSON, up to parse.
Yep.
So we're essentially using this to loop inside of the parse function. So this is kind of a form of continuation passing, I would say, in that we are sort of getting what was parsed and then we are looping until we've exhausted the input, so to speak.
And we know we've exhausted the input when it returns never, and we can probably see that's one of the cases here.
Yes.
Is that I mean, I guess they could have written it like, I'm gonna hope that I don't screw something up here. Maybe they could have written it like that and it would still function the same.
Yep.
Because it returns never, so then we can get rid of this whole block, I think. Yeah, look at that.
Oh, right.
Yeah, so it's kind of an implementation detail, I suppose, but cool.
So we can dive in further about the individual parsers. Maybe.
Yeah, I mean, I guess I have a question. Undefined is not a thing in JSON, is it?
No, it's not. So, this was just a sort of extra. We don't need this case because the test cases don't test for it. Also, it's not valid.
It's not valid JSON.
JSON spec. Yeah.
Yeah. For anyone, like, just to be really clear, what I'm talking about is if you put undefined like there somewhere, it should. I guess the test would pass. If I did that, yeah. So it treats it like undefined as a valid JSON value, but it is not a valid JSON value. Okay.
Yeah.
That's fine.
The objects you can build. Yeah.
So the first one up is parse string. So let's take a look see at parse string.
Yeah. So this is a pretty straightforward implementation of a item that is sort of looping over each character and escaping any like characters that exist, and then using tail call recursion to kind of post-pend that result into its own input, I suppose.
Yep. I see we have L on both sides. We have R on both sides, so they're not really touched. Well, we're just checking this backtick kind of equates to one backtick, and then we're checking if the character that follows is one of the keys, and the keys are just this part, right? And then if it is, then we look up that character to get the actual. So actually, even though this looks like \n, this is a way of encoding a new line into a string. So if I did this, then that's a tab. You can't see it, but actually it's not a tab because I have 2 space on. But anyway, yeah. What is -b and -f? That's return.
Yeah, those are. I think B might be byte character encoding. Yeah.
Oh, okay.
Line feed. I don't know. Yeah, there's a whole bunch of interesting ASCII control characters.
All right.
So there is an interesting aspect to this implementation. So parse string, we're essentially replacing all of the escaped characters with the actual implementation of them. However, what I want to point out is in JSON, we can escape double quotes, right?
Okay.
So
we could put like this.
Or yeah.
Oh, it doesn't work.
Technically, I think you need 2 slashes.
Oh, right.
Yes.
Still doesn't work.
So it doesn't work because there's a bug in this parser.
Oh, okay. You found it? Okay. What's the bug?
Yeah. So if we look at escape cars, there is no escaping supported for double quotes.
Oh, so we would have to do. Okay, can I try?
Yeah, you can try, but there's another issue that will come up that I can talk about.
Oh man, you're like okay.
Yeah.
So that's how I put the double quote there. Or I guess I could have done it like this. I could have done single quote, double quote, single quote.
Yeah.
And then here I'm gonna put the same thing. Okay, but what's the issue that comes up?
Oh, so if we scroll up a little bit, so where we're referencing parse string, the way we're looking for a double quote. You see what I mean?
Mm-hmm.
So that a little bit of additional confusion. So yeah, it's you know.
Well, let's pretend we don't know that that's going on. Okay, that's interesting. Okay, and then let's look at parse array. So same sort of situation happening here. We're kind of inferring the left and right. Like I think grabbing. What's going on here? Okay, so we're getting the rest from there, and then so this okay. Can we like R1 is there, and then like this is R2.
Yeah, a little bit of variable shadowing.
How's it work? Which one is which?
So I think actually, so
is this R1?
So that's R1, and then that's
that's R1.
Yeah, exactly, because
R2 and R2. Yeah. Okay, all right.
Okay, so what we're doing here, we are sort of inferring the first element, or we're inferring the contents of that array, it seems like, and then we're inferring the end of the array. The reason why we have to do it this way is actually pretty interesting. If you try to make it all one inference, the compiler will actually refuse to properly infer the contents of all of the variables. So you're forced to put it in like successive inference statements, like the way we're doing. That's just an element of how it works.
Okay.
So
you couldn't embed another infer inside of the place of what R1 has here.
Yeah, exactly. Yeah.
Got it.
Yeah.
Okay.
So, and then R2 is like kind of the tail after the array. So.
Okay, this is an edge case handling an empty array.
Yeah. I suppose it is. And then we're actually, for parse array, we're passing in R1, which is the actual contents of that array. So all this is doing is we're extracting whatever is in like the next set of quotes, or next set of square brackets.
Okay, so let's go down to parse array. Here it is. So we have our accumulator.
Yep. All tail call optimized, which is great.
You love the tail call optimization thing. I notice you're always, that's like the first thing you look at.
It's very cool. Simple. Once you like have trained yourself to identify it, it's very simple to see whether or not something is doing it, and it's also pretty mechanical to convert a implementation into tail call optimized form. So there's no reason not to do it.
Yeah.
We are. First of all, we're parsing the value. So now we're already in the echelon of recursion because we're referencing parse value, which we already looked at, which eventually references parse array.
Yes, right. Because any value inside the array could be any JSON value.
Exactly.
Okay.
Including an array, right? So we're inferring that value. We know that returns a two tuple, so we're inferring that value. Can
you also escape? Can you escape? Yeah, I guess I could. I'm thinking of ways to break this, but I shouldn't because we're going to get too much in the weeds. But like, you could break this, I suppose, by putting a JSON value that has a comma in it, a string that has a.
We can test it. That is a pretty simple case.
Yeah.
Was it passing before? If we can do this?
That's a great question. What did I break? What did I break? I broke something already. Okay, it must be something about this. A, B, false. No.
It's because line 16.
Oh. Okay. Let's try
now
it
let's
here.
try. Let's be honest.
Oh, it still
No, it
passes. Okay, all right, never mind. Okay.
I think can we? Yeah, I think it'll be robust.
Okay.
Based on my reading. So yes. Yeah. So essentially, we're accumulating into ourselves, and then eventually passing the returning the entire array, which happens on line 142. So line 142 is like the base case of this recursion, and that's parse array.
Yeah, not so bad so far. I'm really digging this solution so far. Okay, and then
this is a very like combinatorial solution. It's very nice. So then finally parse object, which is kind of like the big kahuna, or like the interesting aspect of this problem.
Yep.
So the treatment here is equivalent to how we're treating arrays.
Yep.
We're just
these parts are
extracting.
the same. Yep.
Yeah. So yeah, we can look at parse object to see what the logic changes. So immediately there's another aspect of complexity here in which we need to also convert the object, or we need to maintain the object state as an actual object instead of an array. Adding elements to arrays is very simple. You just destructure, but adding elements to objects are more complicated.
Yeah, we got to bring merge into the picture and all kinds of, merge is for the equals type, but okay.
Yeah.
So there's an intersection in here somewhere. Yeah, right there. Found it.
Yep, exactly. So what we're doing here, we are doing similar logic, but we need to, we need to basically parse what we're doing is we're parsing a sequence of key value pairs. So keys are strings, arbitrary strings. So we should actually be utilizing the full string parser, because keys can have escaped characters in them. Not sure if
but it's not actually using this.
Oh, all right. Maybe another.
Let's try.
Thing
Oh man,
to investigate.
You know what? I don't feel bad. I just gotta say, anybody who's watching this video, I told you in the beginning it's going to be a long one. We're going to take our time. We've had some valid-ish criticism about not taking our time. I think we'll just take our time. So we would do it like this. -T. Oh, it works.
It works. Wait. On line 5, you need 2 double quotes. Not two backslashes on line 5.
Oh, right. Because it's encoding it as a regular string, and then we want to escape it. Yeah, now it does not work. Wait, no,
Yeah.
It would be like this. No, this works.
Yeah, so it works.
Okay.
Yeah, let's go look at how it's working, maybe, because it is interesting.
Parse object. Yeah, here we are.
So parse key. So it's actually in parse key where the logic is. So we need to go to parse key.
Oh, maybe parse key. Oh, there it is. Okay.
Yeah. Okay. Cool. So yeah, we've kind of investigated, and I think we understand the solution more deeply. So we're using the normal string parser, as we should. And then we're on line 165. We say, okay, we've parsed the key. Now we need to parse the colon, and we need to parse the value. So we run parse value as we do
on the trimmed thing.
Yeah, trimming all the inputs. This is just to handle like optional white space that may exist.
Yeah, because someone could come up here and just to scroll to the top, someone could do like, I guess let's go to an object. They could just put a bunch of spaces in there and
or spaces and arrays.
Yeah. It shouldn't matter. Okay.
Indeed. Yeah. So we do seem robust against white space here. And then we are parsing that value, and then we're on line 170. That's our recursive case. So we're just saying, okay, we're going to call ourselves trim any white space, and we're going to inject the key and the value that we've sort of extracted into our own object state. And then,
so the reason this doesn't need to be like deeply finding the key is because we only have passed parse object the segment of the current object that we're working on, and it would get, because of recursion, it would, at a higher level of recursion, it would be summed up.
Yeah.
That makes sense.
Because JSON value is going to also eventually parse an object, right?
Right. Okay. Because I was gonna wonder, like, merge is just a single level merge here. This is not a deep merge.
Yep.
And the reason it doesn't need to be is because every level of recursion, when it hits that last brace, curly bracket or whatever, is it curly brace, curly bracket, I think it's curly brace.
Yeah,
whatever.
curly brace. Yeah.
When it hits the last one, then it will merge. And
yes.
Okay. All right.
Yeah. So interestingly, technically, all the merge is doing is making it look more pretty. If you on line 159, if you replace merge object with just object, all the test cases still should pass.
No, they don't.
They
don't because it's going to be a union. Okay. Let's look at one. See, it's an intersection. So you have so it's like every level has its own intersection instead of each object being summed up. Okay,
I see. Okay,
but you're right that in regular day-to-day life, it like literally cannot matter. It's just to make the equals checker happy. Okay, yes. I think we did a good diligence on this one. It's a different feeling to go so slow on these, but that's okay. I think it's good for us. Good for our. It's kind of nice, actually.
Yeah. Yeah, I think the solution is like very understandable if you take your time with it.
Cool. So that's that one.
But it is wrong.
It is wrong. Okay, yeah, that's true. I was gonna say you're being so nice, and then you said that. Okay. All right. So like check. I don't know. We don't have a checkbox thing, but like we did Alexsey. Now is I don't know how to say this. Omittee.
Omittee.
Is that a way to parse that? Okay. So I'm feeling more confident because I just watched you explain one, but let's go down to 153. So let's go down to the end and see like what's going on. So we take in our string. Great. We're formatting first, parsing value, and then grabbing the first thing. So without looking at anything else, why might you think that would be?
Say again?
I mean, why do you think do you have any, like, without looking at anything else, do you have any hint as to why we might be taking the first of a tuple?
Yeah.
The result of parse value?
That is, well, I already know why, because I already read it. It's because parse value returns a two tuple in a similar way as we did before.
Yeah. Okay.
So
all right.
It's that continuation passing style again.
Okay. So format. Okay, let's go to format first, and we can see what's going on there. So yeah, tell me what you think about format.
Yeah. So format is
here. Line 81. Yeah.
Yeah. So this is interesting in that we are kind of immediately doing a replacement for a bunch of special characters. And the interesting thing is we're doing this on the input without regard for contextual, like what contextual token we are doing a replacement in, which seems potentially hazardous, right?
Yeah.
So what we're doing is we're essentially, regardless of if something is a string or anything else, we're replacing all instances of // R with, the return feed character. So we're doing that. We're also doing some processing on line 88 with regards to curly braces. This seems to be a little bizarre. It seems we're separating out. I think this is like handling white space. we're essentially removing white space so that we don't need to deal with it. So any sort of white space, we're just converting it into an empty string.
Into empty string. Wait, but that's after we've escaped.
Yes.
So that means that if I put, hold on, if I put a, oh, it does work.
It does work. So let's. I think it's in. Let's try to dive in. Let's try to understand why it still works. So it's because. It's because if we encounter, so we're not composing these operations. If we replace a element of a escape character, we don't then subsequently replace it with an empty character, because on line 86, we've already processed that character. You know what I mean?
Oh, okay. That's a termination. That's like end. It doesn't
That's
go.
The
It doesn't
end
get
of
to
this of this character, right? So we don't pass over that character again. So
okay.
So that works.
Okay. All right, I get it. All right, I think I understand. So it's saying like, hey, if you can encounter white space outside of the bounds of these things, like if you're in white space but you've already parsed an array or you've already parsed an object, just remove it. I can't imagine why that's so important. Like, oh, okay, I guess it's important.
Yeah, so it's important in this case, I think, if I had to guess, because they don't have a trim left operation that they're sort of doing everywhere. In the prior example, they had to do trim left everywhere.
All over the place, yeah.
Yeah, so this is kind of a pre-processing step, so they deal with white space only once.
Okay, that's cool. That's cool. I wonder, I bet we could, I feel like it feels dangerous still to me though, even after looking at it, but.
Yeah, it's,
okay.
I would have to think about it further to know if it's correct. But so now we're immediately getting into the meat of things. We are doing parse object. We're doing, so
array.
Interestingly, we're doing object parsing first and then array.
I suppose it doesn't really matter. We could probably do it either direction.
Yeah, often it doesn't matter. Sometimes it does matter for like infinite descent reasons. But
we're seeing if eval is never. So we got to look at eval.
Yeah.
Can we do the easy ones first and then come back to array and object?
Yeah, I think that's best.
Okay. So eval looks like it's evaluating up a literal JSON value. So let's go look at that. Oh, interesting. All right. So.
Yeah, this seems like it's converting.
Okay. This is strings. This is handling strings.
Yeah.
This is handling Boolean and null. This is handling number. V extends number never. So
they're saying we don't handle number, essentially.
Oh, okay. I was going to say, why not handle? I mean, it should work, right? If you just say,
yeah.
No? Okay.
Well, so this is interesting to me as well. If you're fine with like really stress testing this, if we scroll up, if a value happens to be a number, but it is a string, does it still maintain its string status later?
Okay, so let's put there's two B's, but let's use the top level B. So
yeah,
one.
So 1, 2, yeah. And then if we replace
1. It
okay,
still
that
passes.
Works. Okay, cool.
I guess that makes sense because it would still fall into the same bucket with the checking between two double quotes. That does mean though this one is susceptible to double quote. It doesn't allow double quote escaping is not factored into the solution.
Yeah, let's
wanna try that too.
Yeah.
So we can do that, and then oops.
Yeah, I think you. So
oops. There.
So this works, but you need no. So it's because you need two double quotes. Not two double quotes. I mean 2 backslashes, and I can explain why. So.
Right, because it's in a string. Okay.
Yeah, it's in a string, so you need to
escape it for JavaScript.
Yeah.
Okay.
Because we're inside of JavaScript. It's kind of a meta weird string escaping thing, but yeah.
Okay, so it doesn't work. What is the value here? I don't quite know how to read that, but I guess it's saying that it says it thinks it's a backslash double quote is the value. But actually, so then it's expecting that.
Interesting.
It's expecting that. Which is wrong. Is it wrong? No, it's not wrong. Well,
is it not wrong? Yeah. Let's think about this a little bit. So is there a way that we can, I mean, so we're saying, okay.
I think it is correct, actually, because this puts a backslash, this puts a double quote. Actually, why do we need to escape the double quote?
Why would we want a backslash in the output is the thing. So the input we're specifying on line 5 is just a backslash double quote, which in the input, we're just specifying, you see what I mean?
Right. Which still works.
Well, so the input we're specifying on line 5 is just a double quote. We're not referencing it as a
we don't need a backslash at all, you're saying. No, we would. In JSON we would need it to escape it from JSON, but we would have to do that.
Yes. Yeah. And
that's what you've been telling me. Okay, and now it does break.
Okay. Yeah.
Okay.
I think we can yeah.
We spent too long on that.
You don't have to take me at my word. Yeah. We could parse a JSON in like the runtime level to validate. But okay, getting back to the real things.
I guess eval is where we were.
Eval. Okay. So all this is doing is converting
to the literal.
Yeah.
And then we're saying this is an is never check. Then we stop recursing if we got nothing. Otherwise, we pass in what we've evaluated so far and the remainder.
Yep, the rest. Right.
What? Oh, okay. So I guess this is the last recursion is here. This is the base case of recursion we pass in. So that means it doesn't matter what goes in here. Yeah. Oh, it does matter. Wait, why would it matter? Parse value. Oh, if it's for an empty string?
Well, parse value is used by other elements, such as line 135.
Oh, okay. So maybe we should. So let's do it like we said. Let's look at parse array now.
Yes. So, immediately we can tell this kind of the solution is harder to sort of grasp than the last one we looked at.
Yeah.
In that this one is performing some complicated logic involving like commas to handle those in the array. And then we're recursing down to parse value. And then so this is very fascinating. So on line 135, we're parsing the value. And then we're saying, okay, so we have we're inferring that what the value we parsed is. And then if we're saying that, then we go into parse array again. So, but does that allow us any chance to parse an array of an object? Would be a question.
I think it's in the test, right? There's an array
that has an object. Yeah.
Yeah.
So yeah, that should be fine.
Where are we? Here.
Okay. So yeah, somehow we're handling that kind of confusing aspect.
Oh, and it also, is this a valid thing in JSON? Can you there's no trailing commas in JSON. This handles trailing commas. That's kind of cool.
Yeah.
I wish there were trailing commas in JSON.
Yeah, that'd be convenient.
Let's put one in. No, it fails.
Oh.
Wait, was it already failing? Wait a second.
Because we have the...
because we had the thing. Okay.
Yeah.
Let's do this. Great.
And then
let's put a trailing comma here. It passes.
It works.
That's cool. It handles trailing. That's an easy addition,
right?
actually, to handle trailing commas.
Yes.
And it does it for objects, too. Wow. I like this person. Okay. All right.
And then parse... I mean, this is kind of the parsing the array aspect of it. It seems we're like parsing each individual item in the array.
Mm-hmm.
Oh, okay. I see. I understand now. So the parse array we're doing on line 139 is merely to enumerate all of the elements of the array. So as we basically look up to the next comma, and then
Mm-hmm.
pass the output back into ourselves, into the res accumulator on line 128.
Until there's no more commas and there's nothing left.
Exactly. Yeah.
In which case, so when would this never case be hit here? Does this matter? Yeah. It would be hit. Well, when do we check that parse array is never?
We check that sort of at every step because we need to evaluate whether.
Yeah, we have to evaluate. Okay.
Yeah.
All right. That makes sense. All right.
Okay.
So that's we got parse object. Yeah.
So similar structure here to the parse array. As we have, discussed prior, it's just on line 122 instead of doing a very variadic destructuring, we are doing an intersection operation, which then in our base case.
Oh, interesting. We're passing K through. So does that mean that this will allow? Okay. True. And then let's call this true.
Well, it's not a valid object, right?
Oh, interesting. Well, I'm just saying because it passed it through eval, it must have been caught in a prior step.
Yeah.
Because passing the key through eval there, I mean, eval is just the general JSON value, parser. So, okay, it's checking up here. It did it and said, does it or Boolean or null?
Yeah.
Okay, that's where that check came from. Okay, but if we were to take that check away, it doesn't pass anymore. Okay, anyway, that's why it didn't go. But all the same.
Okay. Yeah. Nice. Yeah. Nice to understand. And then one other aspect. The base case is on lines 111 through 114. So we're omitting res never from res, which is interesting.
I want to just see what happens if we don't do that. We get a bunch of records that haven't been merged.
Okay, interesting. Yeah, so there's some sort of like post-processing cleanup step.
What is that? How does that work? Omit never from res.
So I think this is just omitting all of the keys which happen to have a value of never.
Which maybe we would hit. Okay. All right. That actually explains what I was wondering earlier, because that could happen if we hit a situation. That's why I couldn't flip these things on eval, because then we're actually depending on the key to evaluate to never, because that key goes into this record. After we merge them all, we need to take all those keys out. Okay.
Yeah. So this one is but I think we did cover this one, but definitely the logic is a little more global. But I think it might be more efficient than the last one we looked at, because it's not having to parse. It's not having to do that trim left thing everywhere.
That trim left guy, I mean, let me grab it and put it on the screen. I mean, we kind of just like zoomed over it, but that trim left guy has recursion. Here, I'll just put it randomly on the screen. There's recursion in trim left. So on a per character basis too.
Yeah.
So like that ain't good from like a performance standpoint. If it's possible to avoid, it's kind of nice to avoid it. So yeah, I mean, gold star, I think, for this person. All right, next up, any closing thoughts on that while I grab the next one?
No, quite understandable.
Okay, sweet. This next one, they get longer as we go. So the next one here is gets down to line 333. So let's put a check on omittee. So this one is flyFatSeal.
Wait, you do understand the pun for omittee, right?
I mean, I get what omittee is, but like, what is tea? Like the drink?
No, like it's a TypeScript thing. Like omit, like we're passing the type T into omit, right?
So
Yeah, I don't know. It's just a.
I don't get it. No, I mean, like,
Okay,
is
never
there a
mind.
punchline that I just didn't hear?
No. It's just clever. Like
If it was pict, would it be any different?
no. They just like TypeScript, I guess.
I guess the
based
drink
their
is spelled
entire-
TEA.
Yeah.
Omittee. Okay, I don't know. That's more funny to you than it is to me, I guess. All right, so we're getting into some lingo here. This is a JSON parser implemented to a context-free grammar. Mike, what the heck is a context-free grammar?
Yes. So yeah, the concept of grammars is a very fundamental one in computer science that people can, perhaps go to a course for. There exist lots of different types of grammars. Luckily, JSON is easy to parse. I'm not sure that JSON is context free. I don't know. I'm not like an expert in this context, but essentially what we're looking at here is a formal specification for the structure of JSON from a BNF perspective. BNF stands for Bacchus Now Form, and it's like a specification language that people use for parsers. So what we're essentially saying on line 75 is JSON is going to be an object or an array. And then we're saying an object is a open curly bracket, followed by some value, followed by a close curly bracket, et cetera. So we're defining the structure of this problem in this sort of like domain-specific language representation. From the top level all the way to the bottom level. This can be called like top-down parsing as well.
Okay. I mean, I guess I would presume that if someone can implement they claim to be a context-free grammar, that would mean JSON is also context. I mean, context-free means you don't need a unbounded look-ahead, right?
You sound like you know what you're talking about. So yeah, I guess so.
I just play one on TV. No, I don't know. Okay, well, let's look at parse. So parse is on the line 131, somewhere kind of in the top-ish middle. We got a couple things that we're kind of wrapping in here. So we have, maybe I'll break them onto their own lines for funsies. So we have that guy, pure. I bet you, pure is probably a like merge, except it's a deep merge. Okay, so we have a hint already as to what's going on because we saw something similar before. We should probably start with tokenize first.
Yes. So immediately we're kind of doing something interesting here in the realm of parsers, which is we're separating out our parsing into two different steps. We're first doing what I believe is called lexical analysis to convert our string into a array of tokens. These tokens are strings themselves, but what we're doing is we're essentially like removing all of like the white space and all
the
of
trivia.
The trivia. We're removing the trivia of it, such that then the parsing step becomes a transform between an array of tokens to a like actual object.
So does that mean, I was correct. So I was going to ask, that means that we would not expect parse literal to appear anywhere in the path of tokenize because it's like a completely different step.
Exactly. And
we see that to be the case. Yeah. Okay. So then we can think through these. Yeah. All right. I see what's going on. So let's learn what the tokenization turns it into.
Yes.
All right. So here it is. I can't fit it all on the screen, but sorry everyone. But we have S is the input and T is a token array, for better or for worse. That's a little confusing because we usually use T, but oh well.
Yeah. And token array is our accumulator, so to speak.
Mm-hmm. Okay.
Yes. So
we're grabbing the first character. Or,
yeah,
okay, were you going to say something broadly? Go ahead.
I was going to say what I like to do as well for things like this is to find the base case. So where are we returning T directly? And it's at the end.
Yeah, 164.
Okay, so we know that all of the other calls to tokenize are like the recursive call, like the recursive cases, and this is the base case. If we didn't have a
Oh,
base case,
that's an interesting point. Yeah, that is how that works, isn't it?
Yeah.
There's a question mark tokenize at the end of every tree, or never at the end of every tree.
Yeah, so it has a very simple sort of meta structure in that we're either sort of calling to ourselves to process more input, or we're returning like the base case output.
Does that mean this is tail call optimized?
It does mean that it's tail call optimized.
Mike, I'm learning. It only took about 45 hours of intense training, and I'm starting to get it.
Yes.
Okay. And this would happen, like it would return T if there are no more characters left to infer. That's
yes,
yeah.
Exactly.
Okay. All right.
Yeah. So we're checking, okay, is this a special character that we need to handle in an interesting way?
Mm-hmm.
If it is, we treat that as its own token. So we separate out all instances of like commas into just individual characters. So that's what we're doing here.
And we append it to the end.
Yeah, and we append it to the end. So next we're saying, is it a quote? All right, so if it's a quote, that means we need to parse a string. So that's what we do. The string parser returns its first element is the rest of the input that it didn't parse, and the second element is what it returned. So that's what we're doing here.
Mm-hmm.
Then we are merely passing that into tokenize. So we're computing the rest of the input, and then we're passing token to ourselves, and we're also
wait, didn't we lop off? Okay, wait, I'm confused. When we did first, that means rest is like a thing that does not contain the first quote.
Yes, but we don't need that first. We don't need that first quote because we already know it's a string. Like that first quote will never.
But then we're checking here infer. Oh, okay. Parse string result we haven't looked at. Okay, I'm sorry.
Yeah.
So, just a quick question before we keep going. Does this mean that this handles this parser handles a top level array? I think it does.
I think it does, which in most modern specifications of JSON, any JSON value is a valid JSON document.
Including number and string and Boolean and null.
Exactly. Which is a point of contention and is actually not in correspondence with the BNF specification we looked at the beginning of this solution. Mm-hmm. Because it explicitly defined JSON as only a object or an array. But that aside, so we're parsing that string result. We can look into maybe what parse string result.
Yeah, let's jump down. It's above us. Wait, parse. Oh, it's in the very, very bottom. Okay. 312. Parse string result.
Yeah, so we're doing our normal escaping logic, it seems. We're handling. We seem to be
we're escaping right out of the gate.
Yeah.
We're checking for the escape character. We have this escape character helper, and okay, it's very similar to what we've seen before. They opted for not using an object and indexing into the object. This is like the same thing, though.
Yeah, I would say the object indexing is probably more efficient.
And I think it's easier on the eyes too.
Yeah.
But this is good. I'm actually, to break up the monotony for a second, I'm going to make a video I've decided on titled In Defense of Nested Ternaries. And this would be a good one to show that, like, sometimes there is a way to rewrite it where you don't have to have the nested ternaries. But, like, and a minute ago, you also mentioned something like it referred to it as a switch statement. But, I mean, of course, there's no switch statement in TypeScript's type system. It's just ternaries. But you can create something that sort of, this feels, even here, this feels like sort of like a switch. Is it N? Then do this. Okay, is it R? Then do this. Is it F? And that's what a switch statement is. You can even build fallbacks, rather, into this. But, I mean, the basic case I'll make in that video is like, the language of the type system is a different one than the language of JavaScript. it's an expression-only language. And when you have expression-only languages, there is no other option than nested ternaries if you have anything more than one condition. And due to business cases, you very frequently have more than one condition. So like if you look at Perl or you look at, I don't know, any functional like language that only has expressions, it's very common actually to see code that looks a lot like this thing in front of us here. Sometimes there's syntax sugar that will like make it go away, but in a way that's all a case statement is. It's like syntax sugar around nested ifs, and ifs can be rewritten as ternaries. So like it's not a world apart, but anywho,
yes.
That's the sidebar. Okay.
I love it. So we are, handling those escapes. Then we're just passing that result to, we're appending that to ourselves. We're passing the result back in a string in our base case for some reason. It seems we're discarding this at the end, but that is probably fine.
Why are there double quotes in here? Why does it include re-include the double quotes?
Yeah, that's an interesting aspect that I was wondering about. I'm not sure. We would have to look at where we're using parse string result.
I mean, this is the base line 319. This is the base case of recursion, right?
It is. It is, yeah. It's the only base case. So
parse string. Okay, let's go up a little bit and look where parse string result is used. Oh,
yeah.
Okay, this answers the question I asked before. How come we have double quotes here, even though we took it out? It's because parse string result happens to add them back in.
Yeah. So why does it? Can we just remove these two steps and kind of?
Okay, let's try. All the tests passed. Let's just try real quick. We don't need that stuff then. And then let's go here and let's do this. Let's see what our error is. So token. String is not assignable to type token.
Oh, then you cast it.
Okay.
No. With the cast utility.
I don't want to use the cast utility.
Okay, that's fine.
Get away from me with that cast utility.
Well, so we can say token extends string ? Token.
Why do we need to cast it if we've already said here that it extends string?
This is why I don't use this extends. I don't know is the simple answer. Yeah. We need to do some sort of check for some reason.
Is it like redeclared somewhere? No. Token. We can say T, or like, let's just name this X. There's not like a name.
No, it just doesn't know X as a string for some reason.
Oops, we'd have to put X here. Okay, undo. All right, we tried.
Yeah, we tried. Anyway, so we've answered the question of why it is this way. So, and then we're handling a leading new line, which is interesting to me. So we're saying if it has a new line, then we just return never, which I think is correct.
Oh, because we want to error on string. Yeah, strings can't have new lines, like actual new lines. They're not multi-line strings in JSON, like YAML and okay.
Yeah, so this is actually valid and correct.
That's cool.
Yeah, it's also important to fail when you need to fail, rather than only passing when you need to pass. So then we are, this is actually very simple. We're just saying, okay, we're going to parse the next thing. Like, it's doing nothing.
Just keep going.
Yeah.
Okay, is this tail call optimized? No, it's not, because this here returns...
No, this.
Oh, that's the base case.
Yeah, that's the base case.
Okay.
There is a potential optimization that we can do, I believe. Line 322 to 324 is very simple, right? All we're doing is we're saying, no. We are actually doing something real. We're swapping the order of these.
Yeah, that's what I was just going to ask you. It's not. It looks like it's first rest, but it's not.
Yeah.
And it's not even rest. The rest gets passed in here, but result is what comes through the accumulator.
So this is interesting to me. We're doing this sort of reversing process at each step. Mm-hmm. So why does the output not get reversed? Can we make another type, like type foobar equals parseString result, and try to pass something in?
String result.
String result, not primitive result.
Oh, sorry. Autocomplete. Do you have the live code, right?
Oh, yeah, I can modify this.
I mean, yeah, let's do it together. Foobar. I don't have the I don't have the extension. That's okay. It says never. Right.
That is I think that's because we need this maybe. Oh?
Yeah, it's different. So foobar, literal quote, and then 2 literal quotes.
Okay. Oh, okay. I don't understand the precise mechanics of parseString result. It somehow is not reversing its input.
But if you put double quotes here, it would just return the same thing. Oh, that's interesting. Why is it the same? Why is it the same if you put the double quote? I don't know.
Yeah.
All right. Well,
definitely unknowns here. But
what do you say? We'll leave it as an exercise to the reader.
Yeah.
All right. I think we can keep trucking. That was parseString result. Where was it? There. Okay. Oh, why does it keep losing my thing? All right. So that's a string.
Okay. Yeah.
Let's look at parse primitive.
Okay. Yeah. Let's look at it. So.
Also, it's the last thing at the bottom.
Oh yeah. So this is
True, false,
really
null.
simple actually. Yeah, we've seen this all the time. Yeah, we're just in the tokenizer, remember, this parser returns first the rest of the input and then what the result was. So interestingly, we're tokenizing these just as true. So the tokenizer output contains strings, but it also contains literals. That's worth noting.
I guess that makes sense because there's no Boolean. It's only true and false in JSON. There's no Boolean value.
Yes. Well, no. So what I'm saying is so we have the tokenizer step, right? Tokenizer takes in a string and it returns an array. That array it returns is all of the atomic elements, but it's just a flat array. Part of that array is literal true types and literal false types.
Oh, okay. So we might have to do special work to tease those out later.
Yeah. We're not representing them as strings or anything.
Okay, I see what you mean. Okay, yeah. So zooming back up then, where are we here? We didn't look at any of these. We have number type and token. Okay, we didn't see this stuff yet.
Yeah.
So I'm getting a little lost. Where were we?
Okay, we're still in
tokenize.
Yeah, and so we've pretty much finished this. The only thing next is number type. So
number type is just a union. They include this hyphen.
Yes. So I believe this is just saying if there is a number in the input, we just don't handle it at all.
I have a way to break it, I think. Oh, we just don't handle it at all, you're saying? Oh, wait, really?
Yeah, we just return never. Yeah.
Oh, okay. I was going to say, because this doesn't include... this does not include decimals. Right, you can say 1.0. What does this do if you say 1.0? Never.
But it does include, it will see a number immediately because it starts with an integer, and that's not going to be within the confines of the string representation.
Gotcha. Okay, yeah, because we would hit it first. Okay. And then...
So that's all we're handling, and then we're parsing the rest. So we've this is the tokenizer.
And because we put in literal values for the objects, it's kind of like Okay, so we have a flat list of tokens.
We can token. I think it would be interesting to call tokenize manually with an example input and see what the tokenizer is returning.
Okay. Tokenize.
And then some JSON.
I mean, actually, we could just, you know what we could do? Just do this. And then we can look at our tests.
Yeah, sounds good.
So the test will fail, of course, but let's see what they return. So, okay. Let me make some space here so I can fit it on the screen. Okay, so we have literal opening curly. We have double quote A, double quote. Yeah, I think it's exactly like you said. It's just a flat list of all of the things, one after the other in order, including the double quotes when there's a string.
Yep. And this is a very, very performant way to write parsers.
Because it doesn't have to do any kind of backtracking.
Yeah.
Later to figure out what something is.
Yep. So it's this is how you would write a very classic parser on the value.
Oh, that's what token is. This type we never looked at it, but we should have, because primitive is null or true or false.
Yeah.
They consider strings to not be part of that list, but that's fine. String is just something that starts and ends with a double quote, and then we got all of our stuff, and numbers are not included.
Yep. Yeah. Tokenizer just returns an array of tokens.
Okay. So then let's go to, what's the next thing? It's called, where is it? Parse literal.
Yeah.
Okay.
So at this step, kind of all of the tokenizing has been done for us. So what we're doing is purely converting a list of tokens into a big object. So in some sense, we are kind of unflattening the entire structure. So yeah, what we do is essentially we first check, is this a simple value, right? Strings are simple values, null is a simple value, and booleans are simple values because they don't recurse. So if it's a simple value, we parse the literal, we call parse literal result of that simple value. So if we go to parse literal result.
Okay. Same check in the generic, but then we're grabbing out string content, unescaped string.
Yeah.
Oh.
So we're unescaping the string. Normal unescaped logic, as we've talked about.
Yeah, I guess it is. It's a lot heavier on the eyes, but I suppose it is pretty normal.
No, this is unescaping. So we've escaped it before, but now we're unescaping. This is a little strange.
Yeah.
I don't quite. So what we're doing is we're saying if it extends //n, just return /n. So that makes sense to me. If we scroll down to escape string.
Okay.
Escape character.
Escape character. Escape character. Yeah, I'm there.
So this is doing the same logic.
It seems kind of like we escaped it and then we unescape it after.
Well, no, I think it's, if I'm understanding correctly, we're doing, even though we're calling this unescaping, we're just escaping, or both are the same step. They're both unescaping. Even though the second one is named.
Oh, because escape chars only gets called in a situation where we already know that we need to escape.
Maybe?
Because we did that check earlier. Okay, look at this. Look at line 315.
Yeah.
Line 315 is like a sort of a parallel to the checks being done here.
It's equivalent, is it not?
Yeah, I mean, maybe.
I think it is equivalent. I think it's doing the same step twice.
Yeah.
And I think that is incorrect. Maybe.
Well, how could we break it?
If we scroll up, I'll tell you exactly how to break it.
Okay.
So on line 5, let's do B just because I don't want to
do it. Let's not repeat
I'll do it. So and I'll explain each step as I go, right? So I'm going to input a a backslash. So this is one backslash, right?
Mm-hmm.
And then we do there is like backslash escaping in the implementation doesn't even have backslash escaping. Anyway, that's fine. So then if I do this, so now I'm entering /n
into the JSON string.
Yeah. So it handles this correctly. Now, what I'm going to say is let's input another slash, right?
Mm-hmm.
And then the proper output of this would be...
Oops. It'd be that, right?
Would be this, but it doesn't pass. Because what it's doing is it's performing that escape operation twice.
Mm-hmm.
So it first converts the /n to
a regular slash.
Yeah, I think
and then leaves it, and then we get n.
Yeah,
like just the character.
Like yeah.
I get it.
Maybe, yeah. Anyway.
No, not maybe. I think you're dead on. Yeah, I mean it's it's looking at the escape of. Well, actually, hold on. Forget about everything we're looking at from a JSON perspective.
From a JSON perspective, the fundamental thing is we're not implementing backslash escapes. Is that a part of JSON, or am I
Yeah. No.
We're not doing it.
That's true. It's not.
Let me look at you can, okay, there's a backslash escape in JSON, right? Yeah. You do //.
Mm-hmm.
So that's not part of the test. So I think it's fair.
Sure.
But if we were implementing // this double escaping would cause us problems, I think.
Mm-hmm.
Anyway, we can kind of move forward.
Where were we? Parse literal result is where we were, right?
Yeah, and then we're doing this like unescaping process, but that's fine. Okay.
Finally, parse result. Okay.
Parse result. Yes.
Objects and arrays. I've been waiting.
Yeah, these are getting longer and longer. Okay. So, so we're converting this token into. So we're saying, okay, the next token is a open curly bracket. If so, we need to parse an object. So let's go to parse object.
Okay.
Parse object result is what it's called.
Yeah.
So here we're looping through each token. And so immediately we see our base case. If we ever come across a token which is in the curly, then we return
what we got.
Yeah. Otherwise we
It's so nice. It's so nice to be able to trust the things that are in the flat array of like, yeah, we don't have to like wonder if this is like some kind of like escape thing or it's like, no,
like
by now,
space,
the only thing that can be that is the end of an object.
Yep. Yeah.
The end of this object even, which is nice. Because we are going to have to recurse, of course, somewhere. But okay.
Yes.
And same thing for the first for the members of the like first is just like the thing inside like the current member of the object, I think.
Yeah. It's a token, right? So the comma token is like special. Like the comma token will only show up if it's syntax like a syntax special comma. So if it's a comma, then we
like we could have just as easily encoded these with like, like some, dot, end object or something. We could have done something like that and put those inside the tuple as well, right?
Yeah. We totally could have. Like symbol, we could have used symbols even.
Let's not get too fancy. Okay, I like it though.
All right, and then this is a little complicated.
Infer lexeme.
Yeah, Lexeme. What a word. I think this is the key. Question mark.
Okay. Yes.
Okay. And then
It has to be because it's the thing between the double quotes. And we know that we have not yet hit, because like by getting to this point, we have not yet hit the like next element.
Yeah.
And it must be the next part. So I bet you pair. Yeah, pair. Pair is going to grab out. Can we look at pair? Yeah. Here it is.
Yeah,
Pair's going to take out, it's going to separate keys and values and make them a tuple.
Yeah, so Lexeme is actually the key value pair. That is what I would name it instead of Lexeme. And then, we're just, so we're, pair is, and pair is also handling, it's also calling set property on result, it seems.
We didn't look at set property yet. Let's do that. So set property. Ooh.
Yeah, we've seen a million times. It's like,
really? Maybe I'm just shot. So what is set property? It's gonna override a particular value at some key.
Yes. So this is actually this handles. So previously we just used merged, which is a simpler implementation of this. So what this so merge, if you have like conflicts, it will just result in never. What this handles is JSONs which have duplicate keys, which are valid JSON. And in those cases, only the last key gets that value. So this is what this is handling. So
that's one of my favorite JSON fun facts to share with people, that not all JSON is valid YAML. Because people talk about YAML as though it's a superset of JSON, which because of this is not true. In YAML, it is literally in the spec against the rules to have duplicate keys, which is probably a reasonable thing. But in JSON, because JSON takes the approach of having as few rules as possible, it just says that you should avoid having duplicate keys, which of course should means you can do it. And therefore, yeah. Oh, well.
Therefore you, can.
But of course, TypeScript does not allow duplicate keys. You can't have an interface with two keys that have the same name.
Yeah, so it'll result in like never. So anyway, so that's what set property handles. So yeah, I think that if we tested this, it would work in the way we would expect with duplicate JSON keys. So kudos. And then, in the base case, we're just returning the full, like the next result, essentially. So we're passing in the current object that we've kind of built up. And then we're setting a new property on this object.
Yeah, and then and that's what p result is.
Yep. And then
we swap them around and we keep going until we exit the object. And when we exit the object, we return never, which would then go up to here. Never from parse result. Oh, then we would be done theoretically. Okay.
Yeah. So we've kind of covered it. We've covered it. Yeah.
Wow.
In all of these cases, you end up like in a strange loop, or you end up like kind of tying the knot, so to speak, and then finally like understanding the like recursive aspect. Because JSON is recursive. You need a recursive parser.
Yep, makes sense. Yeah, because you could nest objects arbitrarily deep. Yeah, it's fun talking about this kind of thing. Like, I think one thing that's interesting about JSON is like we think of JSON as being relatively slow, but there's this project. Let me look at what their current numbers are. But there's this project called SIMDJSON, SIMDJSON, and they can parse. Let's see, how many? 6 gigabytes. It can minify JSON at 6 gigabytes per second. Validate UTF-8 at 13 gigabytes per second, and it can do new line delimited JSON at 3.5 gigabytes per second. So like, JSON can be made to be fast. It can be made to be very fast. Yeah. Okay. Woo! 3 down.
3 down.
1 to go for this video, and then we'll do yours. Okay, how you feeling, Mike?
I'm feeling great. Yeah, I'm interested to see Hydrati's solution.
Okay, yeah. So Hydrati is so am I. Hydrati has 3 solutions up. I looked at them all. I try not to pat myself on the back too much, but like I go to great lengths to format all of these for a couple things. Well, to fit on the screen, but also to like look more normal than compared to the other challenges we've looked at, so that someone can sit down and watch these videos and it's not like total gobbledygook, because of course, people have different formatting and different ways to do things, and that's great, but we're just here to teach. I don't want to get stuck in the weeds. So I looked through all of Hydrati's solutions, and the third one is the most recent one. It was actually posted fairly recently, despite this being a somewhat older challenge, I think, comparatively speaking, I suppose. And I thought this one was the nicest one, so this is what I selected.
I am already so excited by the fact that in the escape array, or in the escape map, he had a backslash. Line
75.
Yeah, he's handling backslash escapes and double quote escapes, it seems, on line 74. So this might actually be correct.
I don't know why the forward would be needed. Are there regexes in JSON?
There's no regex in JSON.
No, there isn't. So why would... Okay. Comments? Does it handle comments?
Ooh, comments aren't part of the JSON standard.
I know, but like, you know...
That would be amazing. I don't think that's what it's going for.
All right, let's see. So we have a couple helpers. We have space. We should probably look at these this time. Symbol token, string token.
So yeah, we're just... T extends symbol.
Okay, this is kind of like the thing I was just suggesting, making a like enums. They just made types.
Yeah. So every token is going to be
has a number.
Yeah, a number, and then the second element is like the underlying actual thing it is, like the underlying literal value, so to speak.
And they handle symbols too. What is a symbol token?
No, symbols is just on line.
Sorry,
yeah,
symbol, not that kind of symbol. Yeah. Sorry, I got to.
Yeah, I was also confused for a second about that. So immediately we see they have tokens. They probably have a tokenizer.
Yep. Eval result. Okay, I think now we can. So tokenize is here. So let's find the entry point of this program. This one goes down to line 224. So I guess not as long as the other one. So we have parse. What is string extends t? Oh, okay. What was?
Okay, no, I know what this is. So usually you do t extends string, but what this checks for is t itself just the type string. Is it like the universal string? If it's the universal string, we return never. Okay.
Yeah, if somebody just did parse like string, literally exactly this. Yeah.
Then it gets never. Otherwise, I think if you don't do this, it might just it could cause a TypeScript error for infinite loop, or it might just crash the compiler.
No, it doesn't. I mean, I don't know.
Then what does it result in now?
It works.
No, at the bottom, if you hover over X, I'm curious.
Never.
Then we don't need that check. Interesting.
Okay.
Fine.
This is an is never check here as well.
Yes.
For tokenize. So I guess we'll get to tokenize.
Eval. So if tokenization fails, we'll return never.
Okay. Oh, right. That's like a failure mode. All right. I'm so excited to show it for you to see it, actually. I did a video with David Blast, the author of Archetype, and he showed me a technique that I think is super clever about creating, returning strings that are themselves the error message in the type. And the thing that's good is it will still fail for a user when they're using it, but it tells them exactly why. Instead of you get never out of parse, and you're like, okay, I don't know why it's saying never. I thought that was really, it's a cool technique.
That is totally possible. You could make a parsing library that just actually returns parse errors, and gives you the, we encountered character X on index, 274.
Yeah, exactly.
Anyway, let's, So we're evaluating the tokenize.
We're tokenizing twice.
Oh, yes. We're not tokenizing the tokenize, though. We just are not setting it to a variable, what I would do here is I would actually introduce an like X or like, exactly. And then I would reuse that. I honestly don't know if this is like any faster or uses less memory or whatever. You need to do one more thing. You actually need to do to extends and then say like array of tokens or something. Or I guess this is fine. Yeah. But
oh, interesting. Okay, well, we'll leave it like it was, but that's I also had that instinct. So eval result.
Yeah, so we're saying extends eval result.
What would you like to look at first? Tokenized eval or eval result?
Let's look at tokenized. Tokenized is going to be super quick. This is essentially equivalent to what we've already looked at. The only difference is...
So we're grabbing character at a time.
Yeah.
If we have an empty string or nothing left, well, an empty string, we just return what we've gotten so far. Okay, I guess that makes sense. But if...
Yeah, the input has been exhausted.
Right, but if there is actually nothing in the first place, then in that case, we return never.
Yes. As well, so we skip spaces. So if it has a space, then we skip it. Any white space, we just remove.
That's cool. We avoid the trim left dance by doing that.
Yep. We say, is it like a weird symbol? Then we begin like we append that symbol token to ourselves on line 115. Then we check if it is a string. Then we take the string from the parser input. And then finally, we parse true, false, and null. So pretty simple tokenizer, as we've seen before. And we can go into take string, perhaps.
I gotta say, I kind of like that this is the first one of the 3 that we looked at, or I guess 4 so far, including this, that doesn't split this out into like a different helper. Yeah. And I sort of, or maybe the first one did. Well, anyway, I sort of like that it's like the guts of it are all here on one little screen, and we can just like look at it and read it and like sip our coffee and try to understand what it does, you know?
Yeah.
Or tea or water. I don't drink coffee, but I imagine someone sipping coffee. Okay, anyway.
Yes.
So
yeah, let's look at the definition of take string actually.
Yeah, because these other ones are pretty straight. They don't really do anything. Simple token. They just return our special thing, whatever it is, like the special tuple.
Yeah.
Okay, take string. Here we are.
All right. So we see equivalent to what we did before, we are escaping. So equivalent to what we've seen before. If it is an escape character, then we access the escape map on line 137 and append that to our own output. If it, equivalent to what we were doing before, if it is a new line, we return never because multi-line strings don't exist in JSON.
Yep.
And if it is a
quote,
then we do that's our base case, I guess.
String token. Yeah. Okay. Yeah. Seems like it is.
Yeah. That's our base case. So we're looping until we find another.
Yeah. Actually, we could tell at a high level that it's a base case because it's the only one that returns an array.
Yeah. Exactly. Which makes me so if we look at
But if it's not a double quote, then we keep taking characters. So this is going character by character.
It is. And then I believe this is robust against it will properly escape double quotes because in our check on line 135, we can check, but just based on this analysis, we're saying if first extends key of escape, and then key of escape we know contains double quote.
Yep.
Then we will escape it on line 137 by replacing it with like a double quote.
Yep. So let's go up and try it.
Yeah, let's try it.
So yeah, you
Yeah, I'll do it.
I don't want to mess it up again.
It's very tricky. So BA, right? So I'm passing in a backslash, and then I'm passing in a
another one, or no, double quote.
A double quote, like that.
Well, I guess you don't need. Why do you need this third backslash?
Because I can't. Or no, actually, I don't need it. You're right.
You don't need it, right? Okay.
Yeah. It's equivalent either way. Okay, so that's fine. So we're passing in backslash double quote, which should just be double quote in the end.
It is,
and it works. This solution is correct. It's like quite, and then as well, if we also saw backslash parsing itself worked. So if we pass in a backslash, one backslash, and then another backslash, this should just be one backslash in the end, which is this is correct. It looks very, very confusing when you look at it this way, but we're properly handling the entire JSON spec aside from numbers.
Wow, I'm impressed. Does it handle? Okay, let's just we didn't see it anywhere. No, it doesn't handle numbers. We saw
it doesn't handle numbers, nor does it handle Unicode escaping. But those were explicitly.
Does yours handle Unicode escaping?
No.
Okay, good. I was gonna say I don't even know how you. There is a way to split. Oh, I don't remember how. There is a way to split up code points in TypeScript.
Ooh.
I think I've seen it. I see so much stuff like this, though. Maybe I'm dreaming. Okay, but anyway, I think I have seen a way to divide the Unicode code points. I don't know how, but I think there's a way. Okay, anyway, where were we? I'm kind of lost now. Can you get me?
Yes.
We were in
the tokenizer. So we're done with the tokenizer.
Oh, we're done with the tokenizer. Okay. So what is the top level thing? Let's go down to the bottom. Okay, parse, tokenize, eval. So we want to look at eval now, right?
Yes, we do.
Eval takes in an array of tokens, and it's a flat list again, same like before. A little fancier than the tokens we had before, but basically exactly the same.
Yep. So let's go to eval. So that's below.
Oh, it's below. Oh, it's just here. Yeah. It's really simple. Wow.
Yeah. So we're actually doing a distributive union.
Oh, that makes sense because I bet you eval primitive will return never. If it's not that's such a. Oh, I love that. Yeah, that's such a good trick. That is
extremely elegant because this is we're not doing t extends. We're not doing that extends switch case. We're just. I really love this.
This is clever.
And I think it's also very performant as well. Because it's just a union. It's we're not doing an extends a huge nested extends block has to take more resources from the compiler than the union.
Other side of the coin is it's gonna run all three of these every time.
That's true. But so we don't know. Will it take depth? Is the issue, right? I think
that's a good point. Let's keep our eyes open when we look at these three helpers. If they exit early, then we'll know why. If they handle the edge case first, then it's obvious. Okay, they handle the edge case first so that they don't have to go do all the work for something that doesn't end up working out anyway. There's a marriage joke in there somewhere. Okay, so I don't get paid for my jokes, so I can make any kind I like. So eval primitive, you want to start there?
Yeah, let's start at eval primitive.
All right. Token split 1, 2, 3. Okay, so 1, 2, 3. If we look at 1, 2, 3, those are going to correspond to 1 is string, 2 is Boolean, and 3 is null. So it's saying if it's any string, Boolean, or null, then great, grab me something. Otherwise, return never. So as predicted, handles the edge case. There's not other cases here, but eval result, we're going to see, I think, let's look at that last because we're also calling it down on line 220. Sound good to you?
Yeah, that sounds good to me. I do want to point out that was also what we just read was also very clever because it also in that same way removed the need for a bunch of extends checks.
Yeah, it's using a union in the left or in the infer. Yeah. A lot of people don't know, like, you can infer like pretty deep inside of things. Like, I think this syntax is not something people know that you can do. You can pass something to a generic, infer from a value of the parameter of that generic.
Yeah,
this is like thoroughly undocumented TypeScript behavior.
Yeah, this
awesome.
Definitely breaks my brain. But when you use it correctly, it's very performant. Okay, so
in my day-to-day, there's a part of our code base that does a thing just like this, and every time I look at it, I'm like, you little stinker. But exactly like you said, it works really well. So, okay. Well, we infer the output and then we can pass it through. Okay, that's eval primitive.
Yes. Okay. So eval array. Let's do eval array.
Okay.
So
token split. Have we seen token split? No, I don't think so. But it's pretty simple. Token split.
Oh, I see.
Oh, okay. It's just taking off the first thing. Okay, that didn't really need to be done. It's only used. I guess it's used a few places. Okay. That's like basically what we were just looking at. You can infer from the result of that thing. It's so crazy that you can do that. But anyway, okay.
Yeah, so, it's a lot better than how I write it, which is using a bunch of casts.
Mm-hmm. Yeah, you gotta stop it with those casts.
Yeah. No, this is actually a really good alternative to using casts. So I may actually refactor some of my code.
Pick some of this up. All right. Yeah. We're all learning. The fact that you learned something through this is like, I'm feeling good.
Amazing. All right. So
we have eval array elements.
Yes. So we're doing a lot here. We're splitting out that token again just to get the first and the rest on line 157.
What's the base case of recursion here? I mean, it's none of these.
There is no clear base case. Either eval result and...
It's got to be this one.
And eval. There's multiple... Well, no, there's multiple base cases. Line 159 will return.
Uh-huh. Yeah.
Yeah.
If it's a simple, if it's just like a primitive inside the array, then we'll eval result will fire and we'll go. But if there's an object like an array or a JavaScript object, then this is the next base case.
Yeah. So this is kind of a code smell to me. Often you can like make it via cleverness. You can make it so there's only one base case, and it like naturally handles the case where there's like 0 elements. But I don't know enough about this to say whether or not that would be possible here.
All right.
So, and then we have one recursive case, which is also optimal often optimal in my view. Is that true? Yes.
Yeah, it's true.
Yeah. Okay. So, that's eval array elements.
Okay. Wait.
It seems to just be converting these into primitives, essentially.
Oh, okay. So
there's a lot of unnecessary steps here.
Yeah, and we could also have folded all of the code of eval array elements just into eval array.
We could have folded all of this eval code into the tokenizer.
I see, to split up the values.
Yes.
So this is like kind of like sort of doing some, it has token split. I mean, I guess it's doing some kind of processing that the tokenizer step didn't do.
I think all it's okay, let's look at eval result. I think that's the missing.
All right, it's time. The time has come.
Yeah, it's time to look at eval result.
What is it? Eval result.
Yeah.
What?
Okay. Yeah. So this is why I'm saying we're doing a lot of unnecessary work. So the reason we're doing all of this processing is just to convert it from that 2-tuple tokenized form into the actual like underlying
Object.
literal,
Type.
yeah, like like true or false or null or string. Yeah, so there's like a bunch of nothing we're doing, unfortunately, in my view.
Yeah, because we could have just returned a union of all of the, like, or an intersection rather. We could have just returned an intersection at every level, like we saw in the first solution and the second solution.
Yeah, I think we're on the same page. Like on line 89 with null token, instead of returning that tuple, we could have just returned null, is what I'm saying.
Mm-hmm. Yeah, because later we have to get it back out to null.
Yeah, exactly. Like, I think all that whole recursive process is perhaps what we're doing.
Okay.
I think so. I do have a request. Let's run the tokenizer and look at its output. I think that will elucidate some.
Let's do it with this one. So let's call this a let's call this T1 actually. Token eyes. So what's this gonna return? Ooh, a bunch of things. Symbol token, string token, symbol token, string token, symbol token, string token. Okay.
Yeah. So it is. Yeah, it looks nice. But so it is working as a tokenizer. But that eval result step, we're converting from these tokens into like the underlying result.
Into an actual thing.
Is my view of it. So in eval result, here's a question. Do we handle objects?
Well, I was just going to say, let's look at the object eval. I think it's eval object entries. Is that the first? Eval object. Okay, so they did the same pattern. Eval object. We looked at eval primitive. We looked at eval array. Last one is eval object.
Okay. Yeah, eval object.
So eval object does the same business. It exits early if we're not in a symbol token that starts an object.
Yep.
Fine.
Nice short circuiting.
And then from here, then we have our object handling code, line 185 and below.
Yes. And we're sort of immediately going into like eval result. So I will say, and eval, I will say like the recursion here is particularly confusing because it's like at each step we could recurse into ourselves again. Perhaps that's true of all of these parsers, but
I guess, yeah. I mean, the recursion only happens on line 200, which is kind of similar. I mean, what I do like about this is that the base structure of the handler is very similar to the structure of the array handler. They have a lot in common. Arrays are a little simpler because objects can have, more than they have keys and values, so you have to handle those. Yeah. Arrays just have values.
Indeed.
But
yeah, in some sense, both arrays and objects are a comma delimited structure that is surrounded by a certain pair of characters.
Yeah, I see what you mean. Yeah, you could think about an object as just an entries array.
Yeah. Mm-hmm. Very similar. Anyway, so yeah, we're same logic as the array. We're just kind of looping through and then building up the output. So the output is the accumulator, and then we are doing this intersection. Yeah. To accumulate into the output.
Wow.
All right.
Okay. I mean, what do you think about? I mean, is there anything else? I guess this line is sort of long. Okay, what is this line? Can we talk about this line? Line 195.
So this is definitely the base case, right?
I don't even know how to read this line. Okay, first of all, you could do this always.
Ooh. Yeah,
you can. Okay. Extends. Infer. It's like... okay, if I was to put parentheses around things, would it go there? Okay. Okay, so we have output and that thing. So we're unioning these things together. Does it extend? And then what? This goes here.
Oh, so
And then-
yeah. Ooh, this is strange. So it's not even the base case.
Well, you probably are not stuck on what I'm stuck on. I'm stuck on the syntax. Maybe it's just a lot of stuff, and I have seen this pattern a lot of times.
No, I haven't. Yeah, no, this is definitely new to me. This is, yeah.
Thing extends, and then we infer, and then we're putting a constraint on what we infer here.
Yeah, so it's, yeah, the way you might read it is that we're checking if infer output does extend something else, but it's sort of like an ambiguous parse for like TypeScript, because extends has 500 bajillion different meanings.
X must be Y or something.
You know what a better way to represent this this constraint is?
No, but I bet you do.
No, I was gonna say cast.
No, I don't want to cast. Stop it. Get away with the cast. It's a running joke now.
Yeah, it is a running joke.
That happened I think the first time we met, right? The first time we did challenges together, you're like, "Oh, I can solve this with a cast," and I was like, "No, you can't. No, you can't."
Then
I'm
I
a little
did.
defensive. You did actually. Okay, so that's what that line means. Wunderbar, and then. Yeah, I mean, I suppose that means you can do like extends any. Oh no, you can't there. But like that means you could put it like, I don't know, lots of places. Anyway, all right. I've just seeing this syntax in this position is weird to me.
Well, it's because it's a constraint on the inference, so it has to be put after an infer.
I get it. And we see that in arrays a lot. I mean, we see that all over the place, but it's weird to see it. I don't know. It's just weird to see it out of arrays.
Yeah.
And maybe that's the way I should say it. It's not normal. It's not typical to see. So anyway, it's fine.
Yeah. And so the constraint we are saying is that output is an object.
Yeah, that's record string unknown. So does that mean I could put our guy here? No. Why does that error?
Object is different from record string unknown. I tend to just use record string unknown. I don't know the subtle nuances between them, but if you're doing like formal bulletproof like type level logic, I just use record string unknown, and that's purely like a heuristic.
Okay. Well, anyway, I guess did we do it? I mean, that's eval. And we covered all three of those.
Yeah, I think we did it. We're
eval
merging
result,
at the end.
now we know. I thought it was going to be scary, but eval result is not scary at all. It's just unwrapping those things so that we can infer it out. It didn't need to be done that way, but whatever. We know that by the end, I guess what's cool about it is by the end, there must be nothing left in the tokenized input.
Yeah.
If we failed, or there is something left, or something we don't recognize, then we would just return never anyway. So whatever. And then we do a one level merge. Oh, this is a deep merge. Why does it?
Yeah.
But it doesn't need to be a deep merge.
It does, because we're not doing a merging step at each level.
Oh, right. Here on line 195, we would have had to do it up here, or somewhere around here.
Oh, I see. Okay, so this is doing something else as well. This is making output into a reusable variable. Kind of. We're like
we can just keep appending.
Well, so this is really, really strange. Can you see where? Oh, sorry. Can you see where I'm
I can.
highlighting? Okay. So this is a variable shadowing. You know what I mean?
Mm-hmm.
Output is a valid type here. When we do infer output, we are making a new type called output.
Yeah, we could call it output 2, and then this is output 2, and this is output 2.
That's output 2. Yeah, exactly.
Okay. All right.
So yeah, so that type shadowing. So what we're doing is we're essentially saying we're assigning output and record key value into output 2 because we need to reuse it in multiple places. So this is a way to cache this result and not have to like copy it between multiple places, which seems like a generally useful technique.
Okay. I'm going to have to get you and Hydrati on a call.
Yeah.
We've learned some things on this solution.
Yeah, so I'd say this syntax, which was very confusing for you, can be mentally translated into we are asserting, we are assigning a new type variable called output2. We are we're saying that it is this type, and we're this type in scare quotes, and then we're assigning it a value of this thing. So that's all we're doing, kind of like in this whole structure. We're like assigning.
And output is an accumulator, so output could have been passed along from an earlier recursion.
Exactly.
And we know that because we pass eval because we pass it as the accumulator. We pass output2 as the accumulator going forward.
Yep. Yeah, and if we weren't doing this, what we would have to do is like copy this and put it in multiple places, which is gross. So
yeah,
the whole point.
Let's see. Yeah. I just want to see just for my own. Yeah, which works.
Yeah, but it's more gross. So, this is like perhaps even more, maybe more efficient. I would presume it's more efficient.
Why?
Cool. Because we're not doing that intersection twice. I don't know. I just have
right, because we use it twice.
Yeah, we use it twice. Yeah.
This is an interesting trick, though, like how to create a temporary value like in place. Okay, I see why you like it now. I think I understand. Because normally we would want to just like to create temporary storage, we would just add generics that we didn't, don't ever pass.
We can't add it up there.
We can't add it up there because it doesn't exist yet.
Yeah. We would have to do all of these like inference checks inside of the like the different generic parameters, which is something I do often. But this is just like a different way to do it.
This is something. Okay. Wow. I'm glad I complained about it, because now so many learnings on this one. Well, that's it. That's that one. So what we're going to do, we're going to take I'm going to stretch, I'm going to stand up. We're going to take a break. That was part one. Let's put a check mark up here. Okay. Hydrati, check. So we've done 4 solutions. We have a 5th yet to come. Mike has prepared HKT tool belt solution, and it's got a lot of cool stuff and a lot of cool concepts. It will definitely be extraordinarily different from the ones we've seen so far. Takes it does the same job, but I think it takes a different approach because we're using a library and there's tools available to us. So please stick around for that. I guess I don't know. I said at the beginning of the video, we'll post it on the same day. Maybe we should wait a couple days after the challenges are over and we could post this as like a present. It almost stands alone to have this thing as its own. So
yeah, I agree.
But we'll record it right now. Okay. So Mike, I'll see you in a second, huh?
Yeah, indeed.